of proving the problem of proving uniqueness. Okay, so we worked this out previously. In the case of a transport equation. Okay, so it's related to that. Okay, and we're going to use essentially a similar technique. Okay, so let's say that we have two solutions, U1 and U2, okay, that are both twice continuously differentiable on the region for X and also the region for T, R and R plus, okay? So say they solve, I'll say the standard wave equation IVP, okay? So UTTJ minus C squared UXX, J is equal to 0 on R and T greater than 0. And we have some non-trivial initial condition on position and velocity. And we assume already that we can get these solutions. So whenever I'm proving uniqueness, I'm saying if a solution exists, okay, if I can prove uniqueness, there's only one solution, okay? At this stage, we're not worrying about existence. We're saying let's assume that we have, you know, at least one solution, okay? And we typically do at this point because we've figured out a method for finding, you know, at least one solution, but you can't be sure that there's not others, okay? So to exclude the possibility of others, we say, well, let's say there was some other solution, and let's take the difference between that solution and the solution that we know about, okay? So by linearity, what can I say? Well, VTT minus C squared VXX equals 0, okay? And this is you know, the same operator by linearity on the same domain. But now I've removed my initial conditions, right? So I have V of X is equal to phi of X minus phi of X, or 0. Vt of X, 0, is equal to psi of X minus psi of X. This is equal to 0, okay? On X is in R, okay? So just by taking the difference of these solutions, the you know, initial value problem for the difference has trivial initial conditions. So you would expect that this is probably going to have a trivial solution, but we need to prove it without a doubt, okay? So the goal is to essentially show that the only solution to this is V of X is equivalently 0. Okay, for T greater than 0 and X in R, okay? It's not enough to just solve this PDE or, you know, plug in, you know, V equals 0 and say, oh, that works as a solution. Okay, that's not a strong enough condition. You have to exclude the possibility that there's other solutions, okay? So the trick is really to use an energy function for V. And the energy function for V, well, it's just going to be the same form that we worked on before. So I'm just going to write the integral over R. That's just from minus infinity to infinity, okay? And so I just have the integral of the square, well, half the integral of the square of the velocity plus c squared times the square of the spatial gradient, okay? dx, okay? And based on the result that I've shown already, okay, I know that this is constant, okay? Assuming what? Well, I have to assume that U1 and U2 are L2 integrable, okay? right? And I have to assume appropriate differentiability and boundedness, okay? All of the conditions that I wrote down before, okay? So assuming that's the case, then I just have this conservation of energy result from before, okay? So that tells me that E of t is constant, and in particular, it's just E of 0, okay? Basically for all t greater than or equal to 0, okay? But what do we know about E of 0? Well, I can work that out, okay? E of 0 is equal to 1/2 the integral over r. What's, v sub t squared at time equals 0? Well, that's 0. V sub x, I'm sorry, I guess v sub t would be here at 0. V sub x is just the derivative of 0, so that's 0. So I get 0 squared. And so this is 0. So that implies that E of t is equivalently 0. Okay. Well, can I know then that v needs to be 0 based on the fact that the integral over that is 0? Okay. Well, I know that this is at least non-negative. Okay. So each of these component parts needs to be effectively 0 almost everywhere. The trouble that I could have is if v was not continuous, right? Because then you could have little points where v was not 0, okay, but its integral was still 0. So the additional condition that we need is, the continuity of v, which we get from this, differentiability condition. Okay. So that's why we need the differentiability condition. Okay. So now, because of differentiability, okay, E of t equivalently 0, okay, essentially implies that v of x xt is equal to 0, and this is equal to v of t xt equals 0, okay? And I know that v of x 0 is equal to 0 by my initial value problem, okay? And so then the only possibility then is that v of x everywhere, okay, v of xt is equal to 0, okay? So this comes from, right, the non-negativity of the integrand and the continuity of vx squared and vt squared, okay, by assumption. Okay, so that's our uniqueness result. Now, we've worked this out for the case of the wave equation. You're going to use something similar when we get to the heat equation. The energy function does not always, clearly represent a physical energy, okay? So it works out nicely in the case of the wave equation, but it's just called the energy functional because it's motivated by this idea that you can get these functionals by thinking about, physical energies of physical PDE. But, a lot of things you write down, energy functionals for, and it doesn't have a sort of a physical parallel, okay? So that's the idea. In the case of the wave equation, we're sort of handed that energy functional because of what we know about kinetic and potential energy. It's not always going to work out that easily for different PDEs. Sometimes you have to try multiple energy functionals, but what you'll see is that the idea is that you need something so that your integrand is always going to be non-negative. You're usually going to have squares or quadratics of derivatives or the function itself involved. And it should, it should resemble something that you can get by, manipulating your PD. Okay. So that's the idea. We'll sort of circle back to that when we do energy function for heat equation. Are there questions about this?
I have a question.
Yeah.
Um, are we able to maybe like use this to bootstrap to say uniqueness on like bounded functions on the entire real line by saying they're like a countable sum of compactly supported functions or something? Is
Yeah,
uniqueness?
I mean, as long as the derivative, well, so you can do things like you can say, well, it's unique up to, a set of measures 0, I guess. The main problems you're going to run into is if you have discontinuities in your derivatives, and then you can say, well, it's unique anywhere that I have a continuous derivative. The boundedness, I guess, you would need on the derivative terms, right? Because those are the ones entering the energy functional. So you might be able to do it that way. Yeah, and I guess that would be what? Then you have just a finite infinity norm in that case. Yeah, so that I think that could work. Yeah. Yeah. Other questions? Okay.
Um,
Yeah.
and in more than one spatial dimension, uh, we replace ux with like the magnitude of the gradient.
Yeah, so we'll see that more when we get to yeah, we'll see examples of that in once we get to higher order wave equations. Yeah, so you see here that um, yeah, right. You're going to have the full gradient here, and so you're going to have to take the dot product of the gradients in that case. Yeah. So that works. And then your integral is going to be over, Rn rather than just R in that case. Yeah. So yeah, I think you have an example like that on homework 3 where you have to handle a case like that. Okay. All right. So I just want to maybe spend the last 10 minutes by setting up the way